For thousands of years, Earth had been slowly warming. Vast glaciers were retreating. Life was adjusting to a gentler world after the long grip of ice. Then, around 12,800 years ago, something deeply unsettling happened. Temperatures suddenly plunged again. In some regions, the cold returned so quickly that a human lifetime may have been enough to notice the world changing around them. The strange part is not that the climate changed. Earth has always changed. The strange part is that even now, nobody can say with certainty why it happened. So what could make an entire planet suddenly hesitate? Imagine a world that had spent thousands of years learning how to survive the cold. Vast sheets of ice still covered enormous parts of the north, stretching across lands that today hold forests, roads, and cities. The air, in many places, remained sharper than anything most people alive now would recognize. Winters were long. Summers arrived carefully, never fully certain of themselves. Yet despite the lingering cold, something important had begun to change. Around 13,000 years ago, Earth seemed to be slowly exhaling after a very long discomfort. Temperatures were rising. Glaciers that had once stood like permanent walls were beginning to retreat, sometimes by only small distances each year, but enough for the landscape to notice. Rivers flowed where ice had once ruled. Open grasslands expanded. In some regions, scattered patches of woodland quietly returned, as if nature itself had started rebuilding after a season that had lasted far longer than memory could hold. To understand why the sudden return of cold around 12,800 years ago feels so unsettling to scientists, it helps to first imagine the strange kind of hope the planet may have been moving toward. This was not a warm world by modern standards, far from it. Much of North America and Northern Europe still carried reminders of the last great ice age. Towering glaciers remained present across Greenland and parts of the Northern Hemisphere. Sea levels were lower than today because so much water was still trapped in frozen form. Entire coastlines looked different. Lands now separated by water were once connected, allowing animals and human groups to move across spaces that no longer exist in the same way. But change had clearly begun. Scientists studying ancient ice cores, lake sediments, and fossilized pollen often describe this period as one of transition. The cold dominance of the Ice Age was weakening. Slowly, the planet appeared to be moving towards something softer. Herds of animals followed shifting vegetation patterns. Mammoths, bison, reindeer, and other Ice Age creatures traveled through landscapes that were gradually changing beneath their feet. Some grasses spread into areas that had once been frozen for much of the year. Small shrubs appeared in places where survival had once been almost impossible. The transformation was uneven and slow, but it was real enough to leave evidence behind for thousands of years. Human groups living through this time would not have spoken about climate in scientific language. They had no charts, no temperature records, no way of measuring centuries, yet they almost certainly understood seasons deeply. Survival demanded attention. A slightly longer growing season, a change in animal migration, thinner winter ice, or new plants appearing where none had grown before, these were not abstract observations. They shaped daily life. For families moving through landscapes in search of food, even small environmental changes could alter decisions about where to travel, where to hunt, or where to rest. In many ways, the world around 13,000 years ago may have felt uncertain but promising. The immense cold that had ruled for thousands of years no longer seemed entirely permanent. Earth appeared to be warming, cautiously but steadily. That is precisely why what happened next continues to feel so strange. Because if the planet had already begun moving toward warmth, if the ice had started to loosen its grip, why did the cold suddenly find its way back at all? If someone had stood quietly beside a river in the Northern Hemisphere around 13,000 years ago, the world may have seemed as though it was slowly beginning to soften. Not quickly enough to notice from one morning to the next, perhaps not even across a single lifetime in some places, but enough that generations might begin telling different stories about winter. The cold had not disappeared. Ice still ruled much of the north. Yet there were growing signs that something enormous was changing beneath the surface of ordinary life. Earth appeared to be warming, and for many scientists studying this period, the direction of change looked surprisingly consistent. After thousands of years trapped in the grip of the last ice age, Temperatures had begun climbing. This warming phase is sometimes described as part of the long transition out of glacial conditions. Huge ice sheets covering parts of North America and Europe no longer advanced as relentlessly as they once had. In many regions, they retreated. Meltwater carved channels through land that had been locked in silence under ice for centuries. Lakes expanded. Rivers shifted course. Landscapes that had seemed frozen and permanent began rearranging themselves. Plants responded quietly but faithfully. Scientists know this, partly because ancient pollen survives inside mud at the bottom of lakes and wetlands, preserving a strange kind of environmental memory. Tiny grains, invisible to the people who once walked nearby, became records lasting thousands of years. When researchers examine these layers today, they often see evidence of changing vegetation. In some places, grasses gave way to shrubs. Shrubs gave way to scattered trees. The movement was slow, uneven, and deeply regional, but the overall pattern suggested something unmistakable. Conditions were becoming less hostile. A world shaped almost entirely by ice was beginning to loosen. Animals noticed this too, though not consciously in the way humans might describe it. Herds moved according to food, water, and season. Reindeer paths shifted. Grazing grounds expanded northward in certain regions. Species adapted to open cold landscapes continued to survive, but they now occupied environments gradually changing beneath them. A slightly warmer season could alter migration timing. Longer summers could mean different feeding opportunities. In ecosystems balanced delicately between survival and collapse, even small shifts mattered. Human communities likely adjusted as well. These were people whose lives depended on reading landscapes carefully. They followed animals, watched rivers, understood terrain through memory and repetition. A place dangerous one decade might become useful in another. A frozen crossing could disappear. A valley once buried under snow might support plants for longer periods each year. Nobody would have said, "The climate is changing," yet patterns would have been noticed. They had to be. Survival itself required attention to rhythm. Perhaps the most important detail is this: nothing about the warming seemed temporary. That does not mean the climate was stable. Nature rarely moves in straight lines. But from the evidence preserved in ice and ancient sediments, the larger direction appeared clear enough. Earth was emerging from deep cold. Conditions across many northern regions were moving toward greater warmth. If someone alive then had tried imagining the future, they may have assumed the ice would continue retreating little by little, century after century. The idea that temperatures could suddenly reverse direction might have felt impossible. Yet this is where the story begins to turn into something far stranger than an ordinary climate shift. Because around 12,800 years ago, the warming did not simply slow. In some regions, it appeared to stop with startling speed. The planet, for reasons still debated today, seemed to hesitate in the middle of becoming warmer. For a brief stretch of prehistoric time, Earth may have appeared to be recovering from something immense. Not healed, exactly, but moving carefully toward a different rhythm. The great cold of the Ice Age had not vanished, yet there were signs almost everywhere scientists have looked that the world was beginning to rearrange itself in response to warmer conditions. Ice slowly retreated from some valleys. Water returned to landscapes that had long remained frozen. Plants spread into unfamiliar ground. In many northern regions, the future seemed to be arriving one careful season at a time. What makes the sudden cooling around 12,800 years ago feel so mysterious is not simply that temperatures dropped. It is that so many clues suggest the planet had already begun traveling in the opposite direction. One of the clearest signs came from the movement of ecosystems. During periods of intense cold, landscapes tend to become simpler. Fewer plants survive. Tree lines retreat. Grasslands dominate large stretches of exposed land. But when temperatures begin warming, the opposite often happens. Variety slowly returns. Ancient pollen trapped in lake beds across Europe and North America suggests that certain plant species had started moving into areas where colder conditions had once kept them away. Small shrubs expanded in some regions. Trees cautiously followed. The changes did not happen everywhere at the same pace, and scientists remain careful about regional differences, but the broad picture feels difficult to ignore. Nature seemed to be adjusting to a warming planet. Water offered another clue. Vast quantities of ice that had once remained stable began melting more noticeably. Glacial lakes formed in places shaped by retreating ice sheets. Rivers shifted their paths as meltwater carved new routes through the land. Coastlines slowly transformed while sea levels began rising, though they remained far lower than today. Entire territories that ancient people once crossed on foot would eventually disappear beneath water. None of this suggests a world becoming colder, quite the opposite. The Earth appeared to be in transition away from the harshest conditions of the Ice Age. Animals also reveal something about this fragile moment. Species adapted to cold still thrived, yet some migrated differently as environments shifted. The borders between ecosystems moved. Areas once too frozen to support certain plants gradually became usable. Food webs adjusted in quiet ways. Predators followed prey, herds followed vegetation. Life, even in difficult climates, tends to reorganize itself around stability, and for a time, warming may have seemed like the new pattern. Human communities were likely responding without realizing they stood near one of climate history's strangest turning points. People hunted according to animal movement, gathered edible plants when seasons allowed, and remembered landscapes through repeated travel. If winters became slightly shorter or ice crossings less reliable, those details mattered. They changed habits, routes, expectations. Small differences repeated across generations can reshape an entire way of living. Perhaps the strangest detail of all is that none of this looked especially dramatic in the moment. There was no single day when people would have announced that Earth had entered a warmer age. Climate shifts often unfold quietly, through repetition, a stream flowing earlier than expected, snow melting sooner, plants surviving longer, tiny changes accumulating into something enormous. That is why the event waiting just ahead feels almost unsettling in hindsight, because the evidence suggests Earth was not standing still. It was moving, slowly but clearly, toward warmth. Then, around 12,800 years ago, something interrupted that direction. The warming did not merely pause. In parts of the northern hemisphere, temperatures appear to have dropped with surprising speed, leaving behind a question that science still cannot answer with complete certainty. What could make a planet reverse course so suddenly? For something that happened nearly 12,800 years ago, the evidence is strangely precise. No human alive at the time left written records. No one stood watching the skies with instruments. There are no voices describing the moment the warmth faded or the cold returned. And yet, scientists studying Earth's climate believe something dramatic truly happened. The reason they can say this with unusual confidence lies hidden in one of the coldest places on Earth, buried deep beneath layers of ancient ice. Greenland, today covered by a massive ice sheet, acts almost like a frozen archive of forgotten weather. Snow falls, year after year, century after century. Over time, fresh snow compresses older layers beneath it. Air becomes trapped. Tiny chemical traces remain preserved. Dust settles into narrow bands. What looks from above like endless white silence slowly turns into something remarkable underground, a timeline. Scientists call these long frozen cylinders extracted from deep ice cores. At first glance, they appear simple, just columns of compacted ice. But inside them rests an astonishing amount of information about Earth's past climate. Every layer carries clues. The ratio of certain oxygen forms, for example, can help researchers estimate ancient temperatures. Small trapped bubbles preserve pieces of the atmosphere from long ago. Volcanic ash can leave marks tied to specific eruptions. Even wind patterns sometimes leave signatures in the dust. Together, these details form one of the clearest records scientists have for understanding ancient environmental change. What surprised researchers most was not merely that climate had changed in the distant past. Everyone already knew climate shifted over thousands of years. Ice ages came and went. Warm periods emerged and faded. The shock came from how suddenly some of these changes appeared to happen. When scientists examined Greenland ice cores covering the period around 12,800 years ago, they found evidence suggesting temperatures in the North Atlantic region dropped sharply over a surprisingly short period of time. Exactly how short remains debated. In scientific discussions, sudden can still mean decades rather than months, but compared to the slow rhythm usually associated with climate history, the shift looked startlingly fast. Some estimates suggest Greenland may have cooled dramatically within only a few decades. In the language of geology, that can feel almost immediate. Imagine a world gradually warming for centuries, rivers slowly reshaping landscapes, plants cautiously expanding northward, ice retreating little by little. Then, instead of continuing forward, conditions reverse. Not forever, but strongly enough that colder environments begin spreading again. Scientists later gave this period a name, the Younger Dryas, named after a cold-adapted flower called Dryas octopetala, whose pollen appeared more frequently in certain sediments as temperatures cooled. Yet naming something is not the same as understanding it. The ice seemed to say the cold had returned. The question was why. This is important because the evidence from Greenland did not suggest a small regional fluctuation or an ordinary bad winter repeated many times. Researchers saw signs of a significant climate shift. In some northern regions, temperatures may have fallen enough to reshape ecosystems, alter seasonal patterns, and challenge human populations already adapting to warming conditions. Still, caution matters here. Greenland is not the entire world. Ice cores provide powerful evidence, but they mostly tell a story about parts of the northern hemisphere, especially the North Atlantic region. Scientists had to ask a difficult question. Was this sudden cooling local, regional, or something larger? And if the signal in the ice was real, what force could have interrupted a warming planet so abruptly? If Greenland's ice had been the only place showing signs of sudden cooling, scientists might have treated the mystery with more caution. Climate can vary from place to place. A frozen region becoming colder does not automatically mean the wider world changed with it, but over time, evidence began appearing far beyond the ice sheet itself. Quietly, in lake bottoms, buried sediments, ancient cave formations, and forgotten layers of pollen, different pieces of the same story started to emerge. The strange part was not that nature had changed. It was that many signs seemed to point in the same direction, at roughly the same moment. One of the most useful clues came from something so small that ancient people would never have noticed it: pollen. Tiny grains released by plants drift into lakes, wetlands, and soil, becoming trapped inside layers of sediment. Because different plants thrive under different conditions, pollen can reveal what kinds of landscapes once existed. Cold climates favor some species, warmer climates favor others. Over thousands of years, these microscopic traces form quiet records of environmental change. Around the period scientists connect with the Younger Dryas, researchers studying lake sediments in parts of Europe noticed something unexpected. Plant communities that had been shifting toward warmer conditions suddenly appeared to reverse direction. In certain places, cold-tolerant vegetation expanded again, tree growth slowed or retreated. Open landscapes became more common where forests had cautiously begun spreading. It was as though ecosystems had briefly stepped backward after beginning to move forward. The flower that later gave the Younger Dryas its name offers a good example. A cold-adapted Arctic plant called Dryas octopetala became more common in some sediment records during this colder interval. Scientists did not choose the name because flowers caused climate change, of course. The plant simply acted like a marker, a reminder that colder environmental conditions had returned strongly enough for cold-loving species to spread again. Lakes told similar stories in their own quiet language. Sediment layers changed, chemical signals shifted. In some regions, lakes showed evidence of altered water circulation, colder conditions, or ecological disruption around the same period. Elsewhere, cave formations known as stalagmites preserved clues about rainfall and temperature patterns, helping researchers compare environmental changes across different parts of the world. None of these records alone could answer the mystery, yet taken together, they made the picture harder to ignore. Something unusual had interrupted the warming trend. Animals likely experienced the consequences long before humans could understand them. Vegetation changes influence migration routes. Migration shapes survival. A colder season lasting longer than expected can reshape entire food systems. For communities dependent on hunting and gathering, environmental shifts mattered deeply, even if nobody understood the larger climate behind them. A familiar valley might suddenly become less reliable. Rivers could freeze differently. Herd movements might change in ways difficult to predict. This does not mean ancient people witnessed catastrophe everywhere. Scientists remain careful here because climate effects varied by region. Some places seem to have experienced stronger cooling than others. Certain environments change dramatically, while elsewhere the signals appear weaker or more complex. That detail matters. The story is not one of a single frozen switch, affecting every corner of Earth equally. Still, the broader pattern continued pointing towards something difficult to dismiss. Evidence preserved in ice, pollen, lakes, and sediments suggested the warming world had stumbled. Around 12,800 years ago, many northern regions seem to have shifted toward colder conditions with surprising speed. By now, scientists had a stronger reason to believe the temperature drop was real, but another uncomfortable question remained waiting. If the signs of cooling appeared in so many places, what exactly do scientists mean when they say Earth's temperature dropped overnight? The phrase, Earth's temperature dropped overnight, sounds dramatic, almost impossible. It invites an image of people falling asleep in one climate and waking into another. But science, especially climate science, speaks in longer rhythms than human instinct usually allows. To understand why researchers sometimes describe the cooling around 12,800 years ago as sudden, it helps to step away from the pace of ordinary life and think instead in terms of geological time. On a human scale, decades can feel endless. Entire lives unfold inside them. Cities rise, languages change, families disappear into memory. But Earth moves differently. Mountains wear down over millions of years. Ice ages can last tens of thousands of years. Oceans shift in patterns so slow that entire civilizations might never notice them happening. Against that background, a major climate reversal unfolding within a few decades or even a century begins to feel surprisingly fast. In some Greenland ice records, scientists believe temperatures in parts of the North Atlantic region may have fallen sharply within a relatively short period. Estimates vary depending on methods and interpretation, and researchers remain cautious about exact numbers. Yet several studies suggest cooling may have happened rapidly enough that a person living through the period could potentially notice meaningful environmental change during a lifetime. Winters might gradually become harsher, growing seasons shorter, ice more reliable in places where melting had begun. Rivers may have behaved differently. The world would not transform overnight in the literal sense, but the rhythm of life could slowly begin shifting in unsettling ways. This matters because climate usually rewards patience. Ecosystems adapt gradually. Species move slowly across landscapes. Even after warming begins, glaciers often take long periods to retreat fully. That is partly why the Younger Dryas continues to fascinate researchers today. It appears to represent a moment when Earth's climate system changed direction unusually quickly compared with the enormous timescales surrounding it. Imagine reading a very long book, where every page changes only slightly from the one before it. Then, suddenly, within only a few pages, the entire story changes mood. That shift feels dramatic not because it happened instantly, but because it happened unexpectedly against a background of slowness. Scientists remain careful not to exaggerate this moment. Overnight is useful as a metaphor, especially in documentaries or headlines, but it can become misleading if taken literally. The Younger Dryas cooling likely unfolded over years or decades, not a single season. Some regions experienced stronger cooling than others. Some ecosystems responded differently depending on geography. Evidence remains strongest in areas around the North Atlantic, where climate systems appear especially sensitive. Yet the deeper mystery survives even after the exaggeration is removed. Because whether the transition took 10 years, 50 years, or slightly longer, the question remains deeply strange. Why would a warming planet suddenly cool at all? Earth had already begun moving away from the harshest grip of the Ice Age. Plants were adjusting. Ice had retreated in places. Water systems shifted toward a warmer future. Then, somehow, the direction changed. The warming paused, and colder conditions returned strongly enough to leave marks in ice, pollen, sediments, and ecosystems across parts of the world. By the end of Truk 2, scientists seemed confident about one thing. Something interrupted the warming around 12,800 years ago, but confidence fades when the next question arrives, because evidence can show that a mystery happened without explaining why it happened. And somewhere between melting glaciers and returning cold, a puzzle still waits in silence. What force could have persuaded an entire climate system to suddenly turn back? If you had lived around 12,800 years ago, you would not have known that the planet was standing near one of the strangest climate shifts in human history. There would have been no maps showing temperatures, no scientists debating evidence, no headlines warning of sudden cooling. The world would simply feel like the world. Familiar rivers, familiar hunting paths, familiar skies. Yet small differences, repeated often enough, may have quietly begun changing everything. To understand whether humans notice the return of cold, it helps to imagine the kind of lives people lived during this time. These were not settled societies with permanent cities or stored harvests stretching far into the future. In many parts of the world, people survived through hunting, gathering, fishing, and movement. Daily life depended on paying close attention to landscapes. Knowing where animals traveled could mean survival. Understanding seasons mattered deeply. Reading weather was not curiosity, it was necessity. People living near the end of the last ice age had already spent generations adapting to difficult environments. Cold itself was not new. Many communities knew how to survive harsh winters, shifting resources, and dangerous conditions. But around the period before the Younger Dryas cooling, the environment in some regions may have begun feeling slightly more generous. Summers perhaps lingered longer. Certain plants became easier to find. Animal patterns may have shifted as warming landscapes opened new grazing areas. Rivers formed where ice had once blocked movement. Small changes repeated across years can slowly alter expectations, even when no one realizes history is unfolding around them. Imagine a child growing up hearing older relatives describe winters harsher than the ones they currently experience, snow that once lasted longer, ice that stretched farther, valleys too cold to cross. Then imagine that same child becoming an older adult only to notice seasons beginning to harden again, a river freezing earlier than expected, familiar migration routes changing, certain foods becoming less reliable. No single year might seem extraordinary, yet after enough winters, people may have sensed that the world no longer behaved as expected. Scientists remain cautious here because direct evidence of human experience is difficult to recover. We do not possess journals from prehistoric families explaining unusual weather. Archaeology rarely preserves emotions. What researchers can study instead are patterns, settlement shifts, changes in tools, alterations in hunting behavior, signs that populations adapted to environmental pressure. In some areas, evidence suggests human groups reorganized movement and food strategies as climates changed. But connecting those changes directly to the Younger Dryas always requires care. Human decisions rarely follow one cause alone. Culture, geography, migration, competition, and survival pressures overlap in ways that are difficult to untangle thousands of years later. What seems likely is this: people probably noticed environmental instability long before understanding anything resembling climate systems. Humans are observant creatures when survival depends on observation. A shorter warm season matters if plants disappear sooner. Stronger winter conditions matter if travel becomes harder. Changes in herd behavior matter if families rely on animals for food, clothing, and tools. Even slight environmental shifts can ripple outward into daily life. Still, there is an important difference between noticing change and understanding cause. A colder pattern arriving over decades would not necessarily feel like a global event. It might simply seem like difficult seasons returning, bad luck repeated too many times, a landscape becoming less predictable. The people living through this moment would not have known that thousands of years later, scientists would debate why temperatures change so suddenly. They would only know the practical question in front of them. If the land is changing again, where is safety now? For people living near the beginning of the Younger Dryas, survival depended less on strength than on prediction. Knowing where food would appear mattered more than certainty about tomorrow. A hunting group could travel for days following familiar migration routes only to discover that animals had changed direction. A place rich with edible plants one season might offer almost nothing the next. In a world without stored abundance, even small disruptions could feel enormous. If temperatures truly began falling again around 12,800 years ago, one of the first places humans may have noticed the change was in the behavior of food itself. Animals rarely stay still when landscapes shift. Herds move according to grass, water, shelter, and season. During warmer conditions, certain grazing areas become more accessible. Snow melts earlier. Plant life spreads into places where survival was previously difficult. But if colder weather slowly returns, those patterns can begin changing again. A valley once useful for hunting might freeze harder for longer periods. Migration timing could shift by weeks or months. Some species might move southward or gather in unfamiliar territory. For hunter-gatherer communities, following food often meant following uncertainty. Mammoths still walked parts of the northern world during this period, though their numbers had already begun changing in some places. Reindeer, wild horses, bison, and other animals likely shaped daily survival for many groups. But hunting success depended on rhythm. People learned when animals moved, where they gathered, which rivers they crossed, and how weather shaped opportunity. A colder environment could quietly interrupt those expectations. Not all at once, perhaps, but steadily enough to force adaptation. A hunting route trusted for generations might suddenly fail. Plants mattered too, though they often receive less attention in stories about prehistory. Wild nuts, berries, roots, seeds, and edible vegetation formed an important part of survival in many regions. Shorter warm seasons could reduce availability. Colder temperatures might delay growth or change where certain species thrived. If familiar resources became unreliable, people would need to adjust movement patterns, experiment with unfamiliar territories, or rely more heavily on different foods. Adaptation likely happened slowly, shaped by observation rather than understanding. Nobody would have said, "The climate is cooling again." Instead, families may have spoken in practical language. The winters feel longer, the animals are harder to find. This crossing freezes differently now. Survival during uncertain periods often depends on noticing repeated details before they become dangerous. Archaeologists sometimes look for clues to these adjustments in stone tools, settlement patterns, and food remains left behind. In certain regions, there is evidence that people reorganized movement or changed hunting strategies during periods of environmental stress. Yet caution remains important. Human history rarely follows a simple explanation. Communities moved for many reasons: competition, population pressure, changing landscapes, or opportunity. Scientists hesitate to blame every cultural shift on colder weather alone. Still, environmental instability almost certainly shaped choices in ways difficult to fully recover today. Perhaps the most unsettling possibility is how ordinary change may have felt while it was happening. Climate shifts do not always announce themselves dramatically. Sometimes they arrive disguised as inconvenience. A river harder to cross, food appearing later than expected, winters growing slightly longer each year until memory itself becomes uncertain. Was the land always this cold? Were summers once softer? Or does it only seem that way now? For people alive during this strange transition, the mystery of a cooling Earth would not have sounded like science. It would have sounded like a question of survival. If familiar patterns no longer lead to food, where do you go next? If you had been born sometime near the beginning of the warming after the Ice Age, there is a chance your understanding of the world would have been shaped by gentle change. Winters might still feel harsh, but perhaps not quite as severe as stories told by older generations. Rivers could open earlier. Certain animals might appear in places once too cold for them. Small signs, almost forgettable on their own, gathering quietly into a feeling that the land was becoming more forgiving. But what if you lived long enough to notice that trend begin to reverse? What if the warmth that seemed permanent slowly stopped arriving? This question sits at the center of one of the strangest possibilities surrounding the Younger Dryas. Could a single human lifetime have been long enough to notice Earth becoming colder again? The answer, according to many scientists, may be yes, at least in some regions. Climate change is often imagined as painfully slow, something unfolding too gradually for ordinary people to feel directly. In many cases, that assumption is true, yet the evidence surrounding the Younger Dryas suggests the cooling may have happened unusually quickly, especially around parts of the North Atlantic. Not overnight in the literal sense, of course. No one would wake to snow where forests stood the day before. But perhaps fast enough that people could recognize patterns becoming unfamiliar during their own lives. Imagine growing up learning when a river usually freezes, only to notice it hardening earlier with each passing decade. Imagine routes once safe becoming difficult, summers shortening slightly, year after year, until memories begin arguing with experience. Humans are skilled observers when survival depends on memory. A hunter remembers where animals crossed last winter. A family remembers which valley stayed sheltered from harsh wind. Knowledge passed between generations becomes a form of protection. That is partly why environmental instability matters so deeply in prehistoric life. Small shifts repeated over time can alter expectations in ways impossible to ignore. Some researchers studying ancient climates suggest temperatures in Greenland may have dropped dramatically within decades rather than centuries. Elsewhere, the changes appear slower or more uneven. Geography mattered. Certain regions likely experienced stronger cooling while others responded differently. This detail is important because no single human experience could represent the entire planet. A family living near the North Atlantic may have felt environmental pressure more sharply than groups living farther away. Even so, the possibility remains difficult to dismiss. Some people alive around 12,800 years ago may have sensed that familiar patterns no longer held. Archaeology occasionally hints at adaptation during changing conditions. In some areas, settlement behavior appears to shift. Hunting practices evolve. Resource use becomes more flexible. None of this proves people consciously understood climate reversal, but adaptation itself can become evidence that something meaningful changed in the world around them. What humans likely noticed was not temperature in an abstract sense, but reliability, reliable winters, reliable migrations, reliable access to water and food. Climate only becomes meaningful when it shapes ordinary life. A colder season repeated too many times changes planning. A familiar place growing less dependable changes movement. Over years and decades, those adjustments accumulate into something larger than weather. Perhaps the most haunting part of this idea is how invisible history feels while people are living through it. No one during the Younger Dryas knew they occupied a chapter future scientists would spend centuries trying to understand. They were simply people responding to changing conditions the best they could. Yet if the cooling happened fast enough for one generation to notice, another question quietly follows behind it. If humans could sense the world changing, what exactly was powerful enough to change it so suddenly in the first place? When people imagine climate, they often picture the sky. Clouds, storms, heat, snow, wind. Yet one of the strongest ideas scientists have for explaining the sudden cooling around 12,800 years ago begins far from the sky, hidden inside the slow movement of the ocean itself. Because Earth's climate is not only shaped by sunlight or seasons, it is also shaped by water, especially enormous currents moving heat quietly around the planet like an invisible transportation system. To understand why temperatures may have dropped so suddenly, it helps to imagine the Atlantic Ocean not as still water, but as a moving machine. Today, warm water travels northward through parts of the Atlantic, carrying heat from lower latitudes toward colder regions. This movement plays an important role in moderating temperatures, particularly across the North Atlantic and parts of Europe. Without these currents, some regions would likely feel far colder than they do now. The process sounds simple at first. Warm surface water moves north. As it cools, some of it becomes denser and sinks, helping drive large-scale circulation patterns deep within the ocean. Scientists sometimes describe this broader system as the Atlantic meridional overturning circulation, though the details are enormously complex and still actively studied. What matters for this mystery is the idea itself. Ocean circulation helps distribute heat across the planet. If something disrupted that movement, climate patterns could shift dramatically. During the period after the last ice age, Earth contained enormous amounts of melting ice. Vast glaciers covered large parts of the northern hemisphere, slowly retreating as temperatures rose. When ice melts, it releases fresh water, and unlike salty ocean water, fresh water behaves differently. It is lighter, less dense, and can interfere with the sinking process that helps drive major ocean circulation. Here, scientists began wondering whether a chain reaction may have unfolded. Imagine a warming world where glaciers are melting more rapidly. Large volumes of fresh water pour into parts of the North Atlantic. Ocean circulation weakens or changes direction. Less warm water reaches northern regions. Temperatures begin dropping again. In simple terms, the system responsible for carrying warmth north may have stumbled. This idea has become one of the strongest scientific explanations for the Younger Dryas cooling. It does not require mysterious unknown forces or dramatic catastrophes appearing from nowhere. Instead, it imagines Earth responding to instability already created by warming itself. A strange paradox begins to appear. The very process of recovery from the Ice Age may have helped trigger a return to colder conditions. Warming could have contributed to cooling, yet scientists remain careful not to present this as a solved mystery. Oceans are extraordinarily complicated. Climate systems interact with atmosphere, ice, geography, and countless feedback loops. Researchers continue debating exactly how strong the circulation slowdown may have been, how much fresh water entered the North Atlantic, and whether timing aligns perfectly with the Younger Dryas event. Some studies support the hypothesis strongly. Others point to uncertainties still unresolved. This uncertainty matters because climate history rarely follows a single, clean explanation. Nature tends to overlap causes rather than obey simple stories. Even if ocean circulation played a major role, scientists still ask difficult questions. Where exactly did the fresh water come from? How quickly did it enter the ocean? Could one disruption truly cool such large regions so rapidly? For now, the ocean explanation remains less like a final answer and more like a carefully constructed possibility built from evidence. Still, after spending so long wondering whether humans noticed the cold returning, a larger realization begins to emerge. What if the force behind the mystery was not sudden violence from the outside world, but something much quieter? What if Earth's own systems briefly turned against the warming they had already begun? To understand why melting ice might cool a warming planet, it helps to picture the ocean as something far more delicate than it first appears. From the shore, the sea can seem endless and unchanging, too large to be disturbed by anything humans or weather might do. Yet beneath the surface, the movement of water depends on balance. Temperature matters, salt matters, density matters. Even slight disruptions, repeated across vast distances, can alter how heat travels around the Earth. During the final stages of the last ice age, enormous ice sheets still covered parts of North America. One of the largest was the Laurentide ice sheet, a frozen mass stretching across huge regions of the continent. As temperatures slowly rose, meltwater gathered into giant lakes trapped near the edges of retreating ice. Some of these lakes were unimaginably large by modern standards. Scientists often focus on one in particular, a prehistoric body of water known as Lake Agassiz. It no longer exists today, but at its height, it may have held more fresh water than all the modern Great Lakes combined. The important detail is not only its size, but what may have happened to it. Some researchers suggest that as ice barriers shifted or weakened, enormous quantities of fresh water could have escaped suddenly into the North Atlantic or nearby ocean systems. Fresh water, unlike salty seawater, floats more easily at the surface because it is less dense. This matters because parts of the Atlantic circulation depend on cold, salty water sinking downward. That sinking motion helps pull warmer water northward, functioning almost like a conveyor of heat. If enough fresh water spreads across the surface, the process can weaken. Water that should sink may hesitate. Circulation slows. Heat delivery changes. In theory, northern regions begin cooling. It sounds almost too simple. A warming planet melts ice. Melted ice weakens ocean circulation. Weak circulation reduces warmth moving north. Cooling follows. The idea contains a strange irony that continues to fascinate scientists today. The return of cold may not have interrupted warming from outside the climate system. Instead, warming itself may have accidentally triggered the conditions for colder temperatures to return, yet simplicity can become dangerous in science. The farther researchers look into the details, the more difficult certainty becomes. Evidence for giant freshwater pulses exists, but timing remains debated. Some studies suggest meltwater routes may not perfectly align with the beginning of the Younger Dryas. Others question whether enough water entered the right parts of the ocean quickly enough to cause such dramatic cooling. Computer climate models sometimes support the freshwater hypothesis strongly, showing circulation weakening under certain conditions. But models are not history, they are tools for testing possibilities. Scientists still argue about which assumptions best match the evidence left behind. Geography also complicates the picture. Cooling signals appear strongest around the North Atlantic region, where ocean circulation changes would make sense. But climate responses elsewhere remain uneven. Some areas seem less affected, others experience different environmental changes entirely. Earth rarely reacts uniformly. A disturbance in one system can ripple outward in unpredictable ways. Still, despite uncertainty, the freshwater explanation continues to hold unusual weight because it connects many pieces of the puzzle into a story that feels physically possible. It explains how a warming world might briefly lose its balance. But even if this idea comes close to the truth, another problem quietly remains. If water from melting glaciers helped trigger the Younger Dryas, why do scientists still hesitate to call the mystery solved? By now, the ocean explanation may sound convincing. A warming world melts enormous glaciers, fresh water pours into the North Atlantic, ocean circulation weakens, temperatures fall. The story feels logical, almost satisfying in the way mysteries sometimes become easier once the pieces appear to fit together. Yet one of the quiet lessons of science is that explanations are not accepted because they sound reasonable. They survive because evidence continues supporting them even after difficult questions are asked. And in the case of the Younger Dryas, many difficult questions remain. Scientists often describe the freshwater disruption idea as the leading hypothesis, not the final answer. That distinction matters. A leading explanation simply means it currently matches much of the evidence better than competing ideas. It does not mean certainty has arrived. Climate systems are complicated enough that even strong theories can contain missing pieces. One challenge involves timing. To explain a sudden cooling event, researchers need evidence showing that large amounts of fresh water entered the ocean at roughly the right moment. In some studies, signs of major meltwater movement appear close to the beginning of the Younger Dryas. In others, the connection feels less exact. Geological evidence rarely arrives with perfect clocks attached to it. Scientists work with layers of sediment, chemical traces, and dating methods that improve over time but still contain uncertainty. A difference of decades or centuries can matter enormously when reconstructing ancient climate events. Another question concerns scale. Was the freshwater release truly large enough to interrupt ocean circulation strongly enough to trigger dramatic cooling? Some climate models suggest yes. Others produce weaker effects or require very specific conditions. Researchers continue testing different scenarios, adjusting assumptions, comparing evidence from ice, lakes, sediments, and ocean records. Climate models help scientists explore possibilities, but no model can perfectly recreate an ancient Earth where countless variables interacted at once. There is also the question of geography. If ocean circulation weakened, cooling should affect some regions more strongly than others, especially around the North Atlantic. In many cases, this seems consistent with the evidence. Greenland shows dramatic cooling signals. Parts of Europe experienced colder conditions, yet the story grows more complicated elsewhere. Some places reveal weaker effects. Others show different climate patterns entirely. The Earth did not freeze evenly. Regional variation forces scientists to ask whether one mechanism alone can explain everything. Sometimes mysteries remain difficult, not because explanations are weak, but because reality may involve several overlapping causes. Nature rarely chooses simplicity. A shift in ocean circulation could interact with atmospheric changes. Ice behavior might amplify existing instability. Feedback loops between land, sea, and weather could strengthen cooling once it begins. The farther scientists look, the more the Younger Dryas resembles less a single event and more a chain reaction unfolding inside a sensitive climate system already in transition. Perhaps the most surprising part of this mystery is not that researchers disagree. Disagreement, when evidence remains incomplete, is often how science protects itself from becoming overconfident. What matters is that scientists continue testing ideas rather than forcing certainty where certainty does not exist. The freshwater hypothesis remains powerful because it explains many clues without requiring impossible assumptions, yet even its strongest supporters rarely claim the case is fully closed, which leaves us in an unusual position. We may have one of the best explanations for why Earth's temperature dropped around 12,800 years ago, and still not know for certain whether it is truly the answer. That uncertainty opens a quiet but uncomfortable possibility. If the ocean alone cannot explain everything, what other forces might have been involved? If the ocean explanation feels incomplete, the mind naturally begins searching elsewhere. Perhaps something happened in the sky. Perhaps sunlight weakened. Perhaps volcanic eruptions darkened the atmosphere. After all, humans have seen smaller climate disturbances happen even in recorded history. A powerful volcanic eruption can cool temperatures for a short time by filling the atmosphere with particles that reflect sunlight away from Earth. Dust storms can shift local climates. Changes in air circulation can rearrange weather patterns across continents. If temperatures dropped so unexpectedly around 12,800 years ago, it is reasonable to wonder whether the answer may have drifted above the ocean rather than within it. Volcanic eruptions are often one of the first ideas people consider when discussing ancient cooling events. The logic makes sense. When certain volcanoes erupt with enough force, they release ash and sulfur-rich particles high into the atmosphere. These particles can temporarily block or scatter incoming sunlight, lowering temperatures at the surface. Modern history offers examples. Following major eruptions, parts of the world have experienced cooler summers, disrupted weather, and unusual agricultural conditions. The atmosphere, though invisible, can change climate more quickly than many people realize. Yet when scientists examine the Younger Dryas, volcanoes alone struggle to explain the puzzle. One reason is duration. The Younger Dryas cooling appears to have lasted roughly 1,200 years before temperatures rose again. Even powerful volcanic eruptions generally influence climate over shorter periods, often years rather than centuries. Multiple eruptions occurring over long stretches might contribute to instability, but evidence for a volcanic pattern strong enough to sustain the Younger Dryas remains uncertain. Ice cores preserve volcanic traces remarkably well through ash layers and chemical signals, and while eruptions certainly occurred during prehistoric times, researchers have not found a clear volcanic explanation matching the scale and timing of the cooling event. Dust within the atmosphere raises another possibility. During colder periods, landscapes often become drier and vegetation thinner, allowing more dust to enter the air. Dust can influence how much sunlight reaches Earth's surface and may interact with weather systems in complicated ways. Some researchers suggest atmospheric changes involving wind patterns, sea ice, and dust could have amplified cooling once it began. This idea is subtle but important. Perhaps the climate system did not require a single dramatic cause. Instead, several smaller processes may have reinforced one another. A weakened ocean circulation cools northern regions. Growing sea ice reflects more sunlight back into space. Atmospheric patterns shift. Dust increases. Cooling strengthens itself. Scientists call these kinds of interactions feedbacks, moments when one environmental change makes another more likely. This possibility matters because it reminds us that climate rarely behaves like a switch flipped once. It behaves more like a network of connected systems. A small disruption can grow larger if enough conditions align. Still, caution returns quickly. Evidence for atmospheric feedbacks exists, but separating cause from consequence remains difficult. Did dust and air circulation trigger cooling, or did they intensify cooling already underway? Did volcanoes play a supporting role rather than a leading one? Ancient climates leave clues, but not complete instructions. Researchers often reconstruct possibilities from fragments scattered across ice, lakes, cave minerals, and sediments. By now, one uncomfortable pattern begins emerging. Every explanation seems to answer part of the mystery while leaving something unresolved. Oceans help explain rapid cooling, but uncertainties remain. Volcanoes explain shorter-term cooling, but struggle with duration. Atmospheric changes make sense, yet may not fully explain what started everything, which raises a question both fascinating and dangerous. If Earth's own systems cannot explain the entire story, could something more sudden, something arriving from outside the planet itself, have played a role? Few ideas surrounding the Younger Dryas have captured public imagination as strongly as the asteroid hypothesis. It sounds dramatic, almost cinematic. A space object strikes Earth or explodes overhead. Fires spread across continents. Dust rises into the atmosphere. Sunlight weakens. Temperatures collapse. The story feels emotionally satisfying because it offers something mysteries often tempt us to want, a single sudden cause for a sudden problem. Yet the closer scientists look, the more careful the conversation becomes. This is where the Younger Dryas story grows, especially important for a truthful history channel, because the asteroid idea is not pure invention, but neither is it accepted scientific consensus. Around the early 2000s, some researchers proposed what became known as the Younger Dryas impact hypothesis. According to this idea, fragments of a comet or asteroid may have struck Earth or exploded in the atmosphere around 12,800 years ago. Supporters suggested such an event could explain several things at once: rapid cooling, widespread environmental disruption, possible wildfires, and even changes affecting animals and human populations. Certain unusual materials found in sediments became part of the argument. Researchers reported tiny glass-like particles, microscopic diamonds, sometimes called nanodiamonds, and traces of metals that they believed might point toward an impact event. In some locations, dark sediment layers appeared around roughly the right time period, leading to speculation about large-scale burning or unusual environmental disruption. To some scientists, the clues looked intriguing enough to deserve serious attention, but intrigue is not proof. The challenge began when other researchers tried repeating the evidence. Science depends heavily on replication. If one study finds something important, other teams should ideally be able to observe similar results using comparable methods. Over time, criticism of the impact hypothesis grew. Some scientists questioned whether the materials identified truly required an asteroid explanation. Others argued dating inconsistencies weakened the timeline. Certain supposed impact markers proved difficult to reproduce reliably across different sites. Evidence for continent-wide fires strong enough to trigger a major climate shift also remained debated. None of this means the idea has disappeared completely. A number of researchers still investigate impact-related possibilities, and debate continues in some scientific circles. But most climate scientists today do not treat the Younger Dryas impact hypothesis as the leading explanation for the cooling event. Instead, the freshwater disruption of Atlantic circulation remains more widely supported. The difference matters because popular documentaries sometimes present the asteroid story with more confidence than the evidence currently allows. That can make the mystery feel solved when, in reality, much of the scientific discussion remains unsettled. There is also a deeper reason many researchers hesitate. Even if an impact occurred, explaining a climate event lasting roughly 1,200 years becomes difficult. A sudden disaster might trigger short-term disruption, but sustaining colder conditions over centuries requires mechanisms capable of lasting much longer. Once again, the ocean returns quietly to the conversation. Some scientists wonder whether even an external trigger, if one existed, would still need Earth's own climate systems to amplify and maintain cooling afterward. By now, the pattern feels strangely familiar. Each explanation arrives, carrying both promise and uncertainty. Oceans explain much, but not perfectly. Atmosphere and dust may strengthen cooling, but may not begin it. An asteroid sounds dramatic, but struggles under scientific scrutiny. And perhaps the most uncomfortable realization of all is this: after decades of research, the Younger Dryas remains mysterious not because scientists have ignored it, but because every answer leaves something unexplained. If certainty still refuses to arrive, Perhaps the real question is no longer which theory sounds best, but why science itself remains unconvinced. At first, it may seem strange that scientists still disagree about something that happened 12,800 years ago. After all, modern technology can look deep into space, map the ocean floor, and analyze tiny particles invisible to the human eye. Surely, if Earth's temperature truly dropped so suddenly, there should be a clear explanation waiting somewhere in the evidence. Yet, one of the quiet realities of science is that understanding the distant past is often less like solving a puzzle with all the pieces present and more like rebuilding a story from fragments damaged by time. The Younger Dryas remains debated not because researchers lack intelligence or effort, but because the evidence itself is incomplete. Imagine trying to understand a storm after nearly 13,000 years have passed. Rivers have moved, ice has melted, forests have disappeared and returned, coastlines have shifted dramatically. Entire landscapes that once held clues now rest beneath oceans or beneath layers of newer sediment. Scientists cannot step backward into the event itself. They reconstruct it indirectly through signals left behind in ice, pollen, lake beds, caves, ancient shorelines, and chemical traces. Each source preserves only part of the story. Ice cores may reveal sudden cooling but cannot explain every regional difference. Pollen shows environmental shifts but rarely explains precise causes. Ocean sediments hint at changing circulation while leaving room for competing interpretations. The challenge is not the absence of evidence, it is the difficulty of connecting different kinds of evidence into one explanation strong enough to survive criticism. This is partly why disagreement persists. A researcher studying ocean circulation may see the strongest answer in freshwater disruption. Another focused on atmospheric processes may emphasize feedback systems involving sea ice or changing wind patterns. A smaller number continue exploring extraterrestrial possibilities, arguing that impact evidence deserves more attention. Scientific disagreement can sometimes sound frustrating from the outside, as though experts simply cannot decide. But disagreement often serves a quieter purpose. It slows certainty. It forces ideas to survive challenge rather than popularity. In mysteries as large as the Younger Dryas, that caution matters deeply. There is another reason consensus remains difficult. Earth's climate is not controlled by one switch. It behaves more like a network where many systems influence one another at once. Oceans interact with atmosphere. Ice affects sunlight reflection. Wind patterns shape rainfall and temperature. Small changes can trigger larger consequences through feedback loops. Because of this complexity, some scientists suspect the Younger Dryas may not have had a single cause at all. Instead, warming after the Ice Age may have destabilized several connected systems at once. Meltwater weakens ocean circulation, sea ice expands, atmospheric conditions shift, cooling strengthens itself. In this view, the mystery becomes less about finding one dramatic answer and more about understanding how fragile balance can become. Perhaps the most important lesson hidden inside scientific uncertainty is that not knowing something does not mean nothing is known. Researchers agree on many essentials. Around 12,800 years ago, temperatures in parts of the northern hemisphere dropped significantly. The warming trend after the Ice Age was interrupted. The colder period lasted roughly 1,200 years before ending. These foundations remain strong even while debate continues over the precise trigger. The unanswered part lies in the beginning. What caused the reversal? Why did warming suddenly stop? That uncertainty can feel uncomfortable because humans naturally prefer complete stories. Beginning, cause, ending, mystery solved. Yet nature rarely offers such neat endings. Sometimes evidence leads us close to an answer without fully allowing us to touch it. And perhaps that is why the Younger Dryas continues to feel strangely alive in scientific conversation today. Not because nothing is understood, but because enough is understood to reveal how much still remains hidden. If certainty stays out of reach, maybe the next question matters even more. What exactly did this colder world look like once the temperature finally changed? When people hear that Earth suddenly turned cold around 12,800 years ago, it is easy to imagine the entire planet changing in the same way at the same time. A single frozen world, snow spreading everywhere, temperatures falling evenly across continents as though someone quietly lowered a thermostat for Earth itself. But climate almost never behaves so neatly. One of the most important things scientists have learned about the Younger Dryas is that the cooling was real, yet uneven. Some places changed dramatically, others changed only slightly. A few regions may even have responded in ways that seem surprising. Understanding where the cold struck hardest helps explain why the mystery remains so difficult to solve. If the strongest cooling happened in certain regions rather than everywhere equally, the cause may also have been regional before becoming larger. Greenland sits at the center of this story. Deep inside its ice, scientists found some of the clearest evidence that temperatures dropped sharply during the Younger Dryas. Chemical signals preserved in ice cores suggest cooling there may have been dramatic, possibly by several degrees Celsius over relatively short timescales. For a climate system, that is enormous. Greenland matters not only because the evidence is strong, but because its location sits near the North Atlantic, where major ocean circulation systems help distribute warmth. If warm water moving north weakened, Greenland would likely feel the consequences strongly. Parts of northern Europe appear to have experienced major cooling as well. Evidence from lake sediments, pollen records, and glacial behavior suggests colder and drier conditions returned to some areas after warming had already begun. Forest expansion slowed in places. Cold-adapted plants became more common again. In certain landscapes, environments briefly resembled earlier glacial conditions more than the warmer future they had seemed to approach. To people living there, the shift may not have felt like a single disaster, but rather a growing unpredictability in seasons and resources. Around the North Atlantic, sea ice may also have expanded, reinforcing colder conditions. Ice reflects sunlight back into space more effectively than darker land or water, meaning that growing ice can strengthen cooling through feedback loops. This matters because climate shifts often amplify themselves. Once colder conditions begin, they sometimes create circumstances that make further cooling easier. Yet even in regions showing strong evidence, caution remains necessary. Scientists still debate exact temperature changes, local timing, and how rapidly different areas responded. Not every location tells precisely the same story. Climate records from thousands of years ago rarely align perfectly. Some preserve clearer details than others. What appears dramatic in Greenland may seem softer elsewhere. This unevenness becomes one of the most important clues of all. If Earth had cooled identically everywhere, researchers might search for a simple global cause. But because the strongest evidence clusters around the North Atlantic, many scientists continue viewing ocean circulation as one of the most persuasive explanations. The geography seems to fit the theory. Still, fitting pieces together is not the same as certainty. By now, the Younger Dryas begins to look less like a frozen moment affecting everyone equally and more like a complicated rearrangement of regional climates. Some places grew colder enough to leave unmistakable traces. Others experienced subtler changes, which quietly raises another question. If the cold struck hardest in some regions, what happened in places farther away from the North Atlantic? Did the rest of the world experience the Younger Dryas in the same way at all? One of the quiet surprises hidden inside the Younger Dryas mystery is that not everyone on Earth seems to have experienced the cold in the same way. This may sound strange at first. If temperatures dropped so dramatically, should the entire planet not have changed together? Yet climate systems rarely move with perfect unity. Earth is not one climate. It is many climates connected through oceans, winds, geography, sunlight, and feedback loops that sometimes strengthen one another and sometimes compete. During the Younger Dryas, the cold appears strongest around the North Atlantic, but farther away, the story becomes more complicated. In parts of Europe and Greenland, evidence points toward sharp cooling. Yet, elsewhere, signals grow weaker, more uneven, or sometimes unexpectedly different. Some regions show environmental disruption without dramatic temperature collapse. Others reveal changes in rainfall rather than obvious cooling. Scientists studying ancient climates often describe this period not as a perfectly synchronized global freeze, but as a patchwork of responses shaped by local geography, and connected systems. North America, for example, did not respond uniformly. Areas closer to melting ice sheets and northern circulation systems appear to show stronger environmental shifts. But farther south, the effects could vary widely. Landscapes changed differently depending on elevation, proximity to water, and regional weather patterns. A colder atmosphere in one region might influence rainfall elsewhere, rather than simply lowering temperature. For people living through the event, environmental instability may have mattered more than numbers on an imaginary thermometer. In some places, familiar food systems may have become less predictable without temperatures necessarily collapsing in dramatic ways. Farther from the North Atlantic, researchers sometimes find evidence that feels less straightforward. In parts of Asia, climate records suggest changes occurred, though not always in identical patterns. Some lake and cave records hint at shifts in monsoon systems or rainfall timing rather than purely colder conditions. In the southern hemisphere, the picture becomes even more complicated. Certain records suggest environmental changes around similar periods, while others appear delayed or weaker. Scientists continue debating how connected these responses were and whether global climate systems transmitted instability unevenly across hemispheres. This unevenness is not evidence against the Younger Dryas. In many ways, it may actually support the strongest theories surrounding it. If ocean circulation in the North Atlantic weakened, scientists would expect the largest cooling effects nearby. Climate disruption would then ripple outward, influencing rainfall, winds, and ecosystems differently across the world. A single cause does not always create identical results everywhere. Consider how a disturbance in one part of a river spreads differently depending on rocks, bends, and flow speed. Earth's climate behaves with similar complexity. What makes this especially important is how it protects the story from becoming too simple. Saying Earth suddenly turned cold captures the mystery, but reality appears more delicate. Parts of the world likely cooled sharply, others shifted in quieter ways. Some regions may have felt the consequences more through changing seasons, drought patterns, or disrupted ecosystems than through obvious freezing. Even today, climate changes rarely affect every place equally. Geography shapes experience. By now, another quiet truth begins emerging. The Younger Dryas was not one single experience shared by everyone alive. It was many overlapping experiences unfolding across different landscapes at once. A colder Greenland, a changing Europe, altered rainfall elsewhere. Human communities adapting differently depending on where they stood, which leads naturally to a deeper question. If climate can change unevenly across the world, why does Earth almost never respond the same way everywhere at once? It may feel natural to imagine climate as something shared equally by everyone on Earth. One planet, one atmosphere, one temperature. If the world becomes colder, surely every place should grow colder in the same way. Yet Earth has never behaved so simply. Climate is less like a single blanket spread evenly across the planet, and more like an enormous network of moving systems, each influencing the others while still responding differently to geography, oceans, mountains, sunlight, and wind. This is one reason the Younger Dryas remains both fascinating and difficult to understand. The unevenness of the cooling is not a problem in the story. It may actually be part of the explanation. To understand why climate rarely changes equally everywhere, it helps to think of Earth as constantly redistributing energy. Warmth moves through the atmosphere. Oceans carry heat across thousands of kilometers. Winds shift moisture. Mountains redirect storms. Ice reflects sunlight. Forests influence rainfall. A disruption in one place does not simply repeat itself everywhere else. Instead, the effects spread outward, shaped and altered by local conditions. Imagine dropping a stone into water. The ripples move outward, but not perfectly. Rocks, currents, and obstacles change their path. Climate disturbances behave similarly. If the Younger Dryas cooling involved weakened ocean circulation in the North Atlantic, scientists would expect the strongest effects closest to where the disruption began. Greenland and Northern Europe may have cooled dramatically because they depended heavily on northward heat transport. Farther away, the consequences would likely become more indirect. Some places might receive altered rainfall rather than colder air. Others could experience shifting wind systems or ecological changes unfolding more slowly. Even today, climate changes rarely arrive uniformly. A warming planet does not warm every location equally. Some regions heat faster, others face changing rainfall or stronger storms instead. Ancient climate shifts worked in much the same way. Earth responds unevenly because every region begins from different conditions and sits inside different networks of influence. Geography matters, oceans matter, timing matters. This idea also helps explain why reconstructing the Younger Dryas feels so challenging. Scientists studying Greenland ice may see sharp cooling signals. Researchers examining cave minerals elsewhere might find weaker changes or delays. Lake sediments can tell one story, while ocean sediments complicate it. None of these differences necessarily contradict one another. Instead, they reveal a climate system responding unevenly to the same underlying instability. What appears confusing at first may actually reflect how Earth behaves naturally. There is something strangely humbling hidden inside this lesson. Humans often prefer simple causes, leading to simple effects. But climate rarely offers such comfort. A warming world can briefly become colder. One region may suffer, while another changes quietly. Small disruptions can grow larger through feedback loops, impossible to notice in the moment. The Younger Dryas reminds us that Earth's systems do not always move smoothly toward the future we expect. Sometimes they hesitate, sometimes they change direction unexpectedly. By the end of this part of the story, the mystery feels both clearer and stranger. Scientists know the cooling was strongest in certain regions. They understand that climate shifts spread unevenly. Yet another puzzle waits quietly nearby. Around the same period the cold returned, several giant animals that had survived the Ice Age began disappearing. Was this only coincidence, or did the changing climate leave marks not only on landscapes, but on life itself? Long before cities, roads, or written memory, the world held creatures that now feel almost impossible to imagine. Giant animals walked across cold grasslands where glaciers still lingered in the distance. Mammoths moved in herds across northern landscapes. Giant ground sloths wandered parts of the Americas. Massive bison, saber-toothed cats, and enormous deer shared environments that looked familiar in some ways and completely alien in others. For thousands of years, many of these animals survived dramatic environmental changes. They endured the harsh cold of the Ice Age itself, which makes what happened near the end of that period feel quietly unsettling. Around the same broad window of time as the Younger Dryas, many of these giant species disappeared. The timing raises a question difficult to ignore. Did the sudden return of colder conditions help push them toward extinction, or is the connection more complicated than it first appears? Scientists sometimes use the word megafauna to describe these large Ice Age animals. Many were already highly adapted to difficult climates. Mammoths, for example, thrived in cold grassland environments, often called mammoth steppe ecosystems, stretching across large parts of Eurasia and North America. Thick fur, layers of fat, and feeding behaviors helped them survive conditions humans today might consider unbearable. At first glance, this creates an interesting puzzle. If mammoths were built for cold, why would a return to colder temperatures during the Younger Dryas necessarily threaten them? The answer may lie not in temperature alone, but in change itself. Climate shifts affect landscapes, and landscapes shape survival. A colder period arriving suddenly after warming had already begun could alter vegetation patterns in complicated ways. Grasslands expand in some regions, shrink in others, water systems change, seasonal rhythms become less predictable. Animals that evolved over long periods often struggle when environments reorganize too quickly. Survival depends not simply on enduring cold or warmth, but on stability. Giant animals usually require enormous amounts of food and space. Even modest environmental disruption can matter. If migration routes become unreliable, if grazing grounds shift, or if seasonal timing changes repeatedly, populations already under pressure may begin weakening. Smaller groups become more vulnerable to disease, changing habitat, and competition. Extinction rarely arrives all at once. More often, it unfolds quietly, generation after generation, until recovery becomes impossible. Yet caution matters here. perhaps more than almost anywhere else in the Younger Dryas story. Scientists remain deeply divided about how closely climate cooling connects to megafauna extinction. The timing overlaps in some places, but not perfectly everywhere. Certain species disappeared before the Younger Dryas began. Others survived long after it ended in isolated regions. Small populations of mammoths, for example, continued living on remote Arctic islands thousands of years later. This detail matters because it reminds researchers that no single explanation fully solves the mystery. Climate alone may not explain everything. Still, the coincidence feels difficult to dismiss entirely. Around the same broad chapter of Earth's history, the planet experienced an unusual cooling event while many giant species vanished from landscapes they had occupied for thousands of years. Whether the connection was direct, indirect, or only partial remains uncertain, but one possibility continues quietly following the story. Perhaps the return of colder conditions did not kill giant animals outright. Perhaps it simply weakened worlds already becoming harder to survive in, which naturally leads to another uncomfortable question. If climate change alone may not fully explain the disappearances, who or what else was sharing those landscapes at the same time? By the time many giant Ice Age animals began disappearing, humans were no longer rare visitors moving cautiously through unfamiliar landscapes. In many regions, people had spread widely, adapting to cold environments with surprising skill. They hunted large animals, understood migration routes, and learned how to survive in difficult climates that earlier generations may have feared, which quietly introduces one of the largest debates surrounding the disappearance of mammoths and other megafauna. Was climate the real cause, or had humans become powerful enough to change the balance of survival itself? For decades, scientists often discuss two broad explanations. One points toward environmental change, the other toward human hunting and pressure. Yet, the farther researchers look, the more the debate begins resisting simple answers. The climate explanation sounds familiar by now. Around the Younger Dryas, landscapes shifted, temperatures changed unevenly, food systems became less predictable in some places. Large animals requiring enormous territory and stable ecosystems may have faced increasing stress. Mammoths, giant deer, and other megafauna survived difficult conditions for thousands of years, but surviving cold is not the same as surviving instability. A rapidly changing environment can slowly weaken populations long before extinction arrives. Smaller groups mean fewer breeding opportunities. Isolated herds become vulnerable. Recovery after bad seasons grows harder. In this view, climate may not have acted like a sudden disaster, but like pressure building quietly across generations. Then there is the human explanation, sometimes called the overhunting hypothesis. Humans hunted large animals for meat, tools, shelter materials, and survival. Giant mammals often reproduce slowly, meaning populations recover more gradually after losses. Some researchers argue that, as human groups expanded into new territories, hunting pressure increased enough to push already vulnerable species toward extinction. In North America especially, the timing between human arrival and megafauna decline has drawn attention. Certain studies suggest disappearances followed relatively soon after expanding human presence, yet caution returns again. Evidence for widespread overhunting remains debated. Archaeological sites clearly showing large-scale mammoth hunting exist, but they are fewer than some researchers expected if humans alone drove extinction everywhere. Many giant species survived alongside humans for thousands of years before disappearing. In parts of Eurasia, people and mammoths shared landscapes far longer than simple explanations might predict. This makes the story difficult. If humans were solely responsible, why did some species persist so long? If climate alone caused collapse, why do extinction patterns vary so much across regions? Increasingly, many scientists lean toward a more complicated possibility. Perhaps neither explanation works alone. Climate shifts may have weakened ecosystems already under strain. Human hunting and competition then added additional pressure. Neither force individually guaranteed extinction, but together they may have become difficult to survive. A shrinking habitat combined with unpredictable food and steady hunting pressure could push populations below the point of recovery. What matters here is not certainty, but interaction. Earth rarely changes through one cause acting alone. A colder climate affects plants. Plants affect animals. Animals affect human behavior. Human movement reshapes ecosystems in return. The Younger Dryas may not have created extinction directly, but it could have altered the conditions in which extinction became more likely. By now, a quiet pattern emerges across this story. Again and again, the simplest answer refuses to hold. The cold may matter, but not entirely. Humans matter, but not completely. Giant animals disappear, but unevenly. Mystery survives because reality seems woven from several causes rather than one dramatic event, which leaves an uncomfortable thought lingering in the background. If ancient humans lived through environmental instability strong enough to reshape ecosystems, what lessons might their world still quietly hold for ours today? If the Younger Dryas changed landscapes, altered food systems, and possibly placed pressure on giant animals, then another question quietly follows behind it. What happened to the humans who lived through this instability? Unlike mammoths or giant deer, people possessed something unusual: flexibility. Humans could move, adapt, cooperate, remember, and change behavior faster than most species around them. Yet adaptability does not mean comfort. Living through environmental uncertainty may have quietly reshaped daily life in ways impossible to fully recover today. Around 12,800 years ago, human communities in many regions still depended heavily on hunting, gathering, fishing, and seasonal movement. Survival often required deep familiarity with local rhythms, which plants appeared at certain times of year, which rivers stayed reliable, which animal migrations returned predictably. Stability mattered because memory itself became a survival tool. Parents taught children where food could be found. Older generations remembered dangerous seasons. Entire communities carried knowledge shaped by repeated patterns in the land. But what happens when those patterns begin changing? Imagine learning a landscape that no longer behaves the same way your elders described. Winters arrive differently. Familiar plants become less dependable. Herds move unpredictably or disappear from known routes. A crossing once safe freezes too early or not enough at all. No single season necessarily feels catastrophic, but uncertainty slowly grows heavier. Human adaptation often begins quietly, small adjustments repeated until they become a different way of living. Archaeologists sometimes see hints of these changes in movement patterns and tool use. In some regions, communities appear to have shifted hunting strategies or broadened food sources during environmental instability. Flexibility may have become one of humanity's greatest advantages. When one resource failed, people experimented with another. When familiar routes grew unreliable, groups moved elsewhere or reorganized seasonal habits. Yet adaptation likely came with difficulty. Every environmental change carries cost. Movement requires energy. New food systems involve risk. Smaller resources may support fewer people. Environmental unpredictability can increase tension between neighboring groups competing for shrinking opportunities. Researchers remain careful here because prehistoric human experience rarely leaves clear explanations behind. Stone tools survive, bones survive, campsites survive. Thoughts do not. We cannot know exactly how people interpreted a colder world returning after warming had begun. They would not have spoken about climate systems or ocean circulation. More likely, they responded practically. The land feels harder now. Hunting takes longer. Familiar seasons no longer feel familiar. In some parts of the world, environmental pressure may even have encouraged experimentation that later shaped human history in unexpected ways. Certain researchers studying the ancient Near East have explored whether changing climate conditions near the Younger Dryas influenced shifts toward more settled lifestyles and food management. These ideas remain debated and vary by region, but they suggest something important. Instability can force innovation. Humans often change not when life becomes easy, but when certainty disappears. Still, caution matters. The Younger Dryas did not affect every human community equally. Geography mattered. Resources mattered. Some groups likely adapted successfully for generations. Others may have moved or struggled in ways archaeology only partly reveals. Yet one quiet truth seems difficult to ignore. Around 12,800 years ago, people lived through a world becoming harder to predict, and perhaps that matters more than cold itself, because survival has never depended only on weather. It depends on whether humans can adapt when familiar patterns begin disappearing, which leaves a question lingering gently at the edge of the story. If ancient humans survived uncertainty before understanding what caused it, what might that say about how humans face uncertainty now? At first, the Younger Dryas may seem like a story safely trapped in the distant past, a strange cooling event long before cities, engines, or modern life. An ancient mystery belonging to mammoths, glaciers, and forgotten landscapes. Yet one reason scientists continue studying it so carefully is because the Younger Dryas does not only ask what happened 12,800 years ago, it quietly asks how stable Earth's climate really is. This is where the story slowly begins moving closer to the present. For much of human history, people naturally assumed climate changed slowly, almost too slowly to notice. Seasons came and went, landscapes shifted across generations. Stability felt normal, but the Younger Dryas challenges that comforting assumption. It suggests that under certain conditions, climate systems may sometimes shift faster than expected. Not overnight in the dramatic sense of headlines, but quickly enough to matter within human timescales. That possibility continues attracting scientific attention today. Researchers studying ancient climates are not simply interested in historical curiosity. The past often becomes one of the best laboratories for understanding how Earth behaves under stress. Scientists cannot experiment on the planet directly at global scale, but they can study moments when climate systems changed naturally before modern technology existed. In that sense, the Younger Dryas becomes something unusual, a lesson preserved inside ice, oceans, and sediment. One reason the event feels especially relevant involves ocean circulation. Earlier in this story, we explored the idea that melting ice may have disrupted heat-carrying currents in the North Atlantic. Today, some scientists continue monitoring major ocean circulation systems carefully, including parts of the Atlantic that influence regional climate. This does not mean researchers expect another Younger Dryas to suddenly appear. That would oversimplify both ancient and modern climate conditions. The world today differs enormously from the world of the last ice age. Ice sheets are smaller. Continents interact with different environmental pressures. Human activity now influences climate in ways prehistoric systems did not experience. Yet studying past instability still matters because it reveals something important about complexity. Climate systems can contain thresholds. Small changes do not always remain small. Sometimes gradual pressure builds quietly before larger shifts emerge. This does not mean sudden collapse is inevitable. Scientists remain careful about dramatic comparisons because ancient events rarely repeat exactly. Still, the Younger Dryas reminds researchers that climate is not always predictable in the smooth, gradual way people often imagine. Another lesson hides inside uncertainty itself. Scientists continue debating parts of the Younger Dryas not because evidence failed, but because evidence revealed complexity. Oceans, atmosphere, ice, geography, ecosystems, each interacts with the others. Understanding climate means understanding relationships, not isolated causes. That challenge continues today. Modern climate research often depends on combining data from many systems rather than expecting one simple explanation to solve everything. Perhaps this is why the Younger Dryas still feels strangely alive in scientific conversation. It sits at the uncomfortable boundary between confidence and mystery. Researchers know cooling happened. They understand many possible mechanisms. Yet uncertainty survives around details large enough to matter. In some ways, the event becomes a reminder that Earth has surprised humans before, not through fantasy or sudden disaster movies, but through quiet shifts unfolding inside systems people barely understood at the time, which leads to an unsettling but deeply human question. If ancient people lived through profound environmental uncertainty without knowing what caused it, are modern humans truly as prepared for uncertainty as we like to believe? When people hear about the Younger Dryas today, a natural question often appears almost immediately. Could something like this happen again? If Earth once shifted into colder conditions unexpectedly, does that mean modern climate could suddenly reverse direction too? It is an understandable question, but also one that requires unusual care, because comparisons between the world of 12,800 years ago and the world today can teach valuable lessons while also becoming misleading if pushed too far. The first thing scientists usually emphasize is that the two worlds are not the same. During the Younger Dryas, Earth was emerging from an ice age. Enormous ice sheets still covered parts of the northern hemisphere. Vast quantities of meltwater moved through changing landscapes. Ocean circulation systems operated under conditions very different from those of today. The climate was already unstable because the planet itself was transitioning between major environmental states. Modern Earth exists inside a different context. Today's climate system includes human influence on a scale prehistoric environments never experienced. Because of this, scientists are cautious about direct comparisons. The Younger Dryas is not treated as a prediction for what modern climate will do next, yet caution does not mean irrelevance. Researchers still study the event because some underlying lessons remain surprisingly important. One similarity involves the idea of thresholds. Climate systems do not always respond smoothly or gradually. Sometimes pressure builds quietly before larger shifts emerge. A river may flow calmly until enough stress changes its course. Ice, oceans, atmosphere, and ecosystems can behave similarly. Scientists studying Atlantic circulation today occasionally ask whether large inputs of fresh water from melting ice could influence ocean systems in meaningful ways over time. These questions do not imply that a Younger Dryas-style event is expected soon. Instead, they reflect a broader scientific habit, studying the past to better understand what kinds of changes climate systems are physically capable of producing. Another similarity lies in uncertainty itself. Ancient humans experienced environmental changes without understanding their causes. Seasons shifted, resources changed, landscapes behaved differently. People adapted without possessing climate models or scientific explanations. Modern societies, by contrast, possess extraordinary tools. Satellites observe oceans, ice cores preserve ancient history. Supercomputers model climate interactions impossible to imagine even a century ago. Yet despite these advances, uncertainty still exists. Climate science often deals in probabilities, risks, and evolving evidence rather than perfect certainty. That discomfort can feel frustrating because humans prefer clean predictions. But uncertainty is not ignorance. It often reflects honesty about complexity. There is also an important difference between fear and preparation. Scientists studying ancient climate shifts are not usually trying to frighten people with stories of sudden catastrophe. More often, they seek understanding. The Younger Dryas reminds researchers that Earth's systems can behave in ways more complicated than intuition suggests. A warming planet once experienced a major cooling interruption. Ocean systems may have amplified environmental instability. Regional changes unfolded unevenly. Nature resisted simple storytelling. Perhaps the most valuable comparison between ancient and modern worlds has little to do with temperature itself. It concerns adaptability. Humans 12,800 years ago survived profound uncertainty without fully understanding what shaped it. They adjusted movement, food systems, and expectations when familiar patterns changed. Modern humans possess vastly greater knowledge, yet still confront uncertainty in quieter ways. The lesson may not be that history repeats itself. It may be that resilience matters whenever certainty disappears, which leaves one final question slowly approaching. If the Younger Dryas still matters today not because it predicts the future, but because it challenges assumptions, what deeper lesson has this strange ancient mystery been quietly trying to teach all along? Perhaps the strangest thing about the Younger Dryas is not the cold itself, not the glaciers, the disrupted oceans, or the unanswered scientific debate. Perhaps the strangest thing is what the event quietly reveals about certainty. Humans often imagine the world as stable because stability is what memory allows us to see. Seasons repeat, rivers follow familiar paths, winters arrive, then leave. Entire societies slowly begin assuming tomorrow will resemble yesterday. Yet 12,800 years ago, the planet seems to have reminded life of something uncomfortable. Stability can feel permanent right before it changes. This may be the deepest reason scientists still return to the Younger Dryas, not because they expect history to repeat exactly, but because ancient climate shifts expose how complicated Earth truly is. For centuries, people viewed climate almost like scenery, a background setting to human life, rather than an active system full of movement and feedback. But the Younger Dryas suggests something more subtle. Earth's environment is not motionless beneath civilization. It behaves more like an enormous living balance, constantly adjusting, reacting, redistributing energy in ways humans often notice only after consequences appear. A warming world briefly turned colder. Ocean circulation may have shifted, landscapes reorganized, animals adapted or disappeared. Human communities adjusted in ways archaeology only partly remembers. None of this happened because the planet was broken. It happened because complexity itself sometimes produces surprises. There is something quietly humbling about that idea. Modern humans often speak as though knowledge guarantees control. Satellites map oceans. Climate models simulate possibilities. Instruments measure details invisible to earlier generations. Yet even now, uncertainty remains part of understanding. Scientists still debate exactly what triggered the Younger Dryas. They continue refining evidence, testing explanations, questioning assumptions, not because science failed, but because good science remains careful where certainty exceeds proof. In some ways, the mystery teaches patience. Not every unanswered question represents weakness. Sometimes complexity simply takes longer to understand. There is another lesson hidden inside the people who lived through this event. Ancient humans likely did not understand ocean circulation, atmospheric feedbacks, or melting ice sheets, yet survival did not wait for perfect explanations. They adapted anyway. Communities moved, diets shifted, strategies changed. Humans responded to instability using observation, cooperation, and flexibility long before scientific language existed. That truth feels oddly comforting. Knowledge matters, but adaptability matters too. The future has never belonged only to those who understand change first. It often belongs to those willing to adjust when familiar patterns stop behaving as expected. Still, the Younger Dryas refuses to become a simple moral story. It leaves questions open. Did one trigger begin the cooling, or several? Was the ocean the main actor, or only one part of a larger chain? Could evidence still buried beneath ice or sediment eventually change what scientists believe today? The mystery survives not because answers are impossible, but because enough uncertainty remains to keep asking careful questions. Perhaps that is why this ancient event continues quietly echoing across time. A reminder that certainty is often temporary, balance can shift unexpectedly, and even a planet moving toward warmth once paused long enough to surprise everything living upon it. Which brings us gently toward the final stage of this story. If so much remains unknown, how should we remember an event that science still cannot fully explain? After traveling through glaciers, oceans, vanished animals, uncertain climates, and unanswered theories, it may help to pause quietly beside the central mystery itself. Because the Younger Dryas can sometimes feel confusing precisely because there is so much information surrounding it: oceans slowing, freshwater floods, ice sheets melting, giant animals disappearing, human adaptation, competing theories, scientific caution. Yet beneath all those details, one simple question has guided this story from the beginning. What do scientists actually know about the moment Earth's temperature suddenly dropped around 12,800 years ago, and what still remains uncertain? Surprisingly, researchers agree on more than people often realize. The first major point is strong. Something significant happened. Around 12,800 years ago, during a period when the world had already begun warming after the last ice age, temperatures in parts of the northern hemisphere shifted sharply toward colder conditions. Evidence for this appears across multiple sources. Greenland ice cores preserve chemical signals pointing toward rapid cooling. Sediments, pollen records, and glacial behavior in parts of Europe and North America show environmental changes consistent with colder conditions returning. Whatever happened, it left marks too large to dismiss as coincidence. Scientists also broadly agree that the Younger Dryas did not last briefly. This was not a single harsh winter or a temporary disruption lasting only years. The colder interval continued for roughly 1,200 years before temperatures rose again. That detail matters because it shapes which explanations seem physically plausible. Sudden events alone, such as a single volcanic eruption or short-term atmospheric disturbance, struggle to explain such a long duration without additional climate mechanisms sustaining the change. Researchers further agree that the strongest cooling appears centered around the North Atlantic region. Greenland and Northern Europe preserve especially dramatic signals, while other regions responded unevenly. Some areas cooled strongly. Others experienced changes in rainfall, ecosystems, or seasonal behavior rather than identical temperature shifts. This unevenness continues shaping scientific debate because it suggests regional systems, particularly oceans, may have played an important role. Where agreement begins weakening is at the beginning of the story. Scientists know cooling happened. They do not fully agree on exactly why it started. The leading explanation remains disruption to Atlantic Ocean circulation caused by large freshwater inputs from melting ice. In simple terms, warming after the Ice Age may have released enough fresh water into northern oceans to weaken heat-carrying currents, allowing colder conditions to return. Many researchers view this as the strongest explanation because it fits important pieces of geography and climate evidence. Yet even this idea contains unresolved questions involving timing, scale, and exact mechanisms. Other possibilities remain debated. Atmospheric feedbacks involving sea ice and shifting wind patterns may have strengthened cooling. Volcanic influence appears less convincing as a primary explanation, but could have contributed indirectly. The asteroid or comet hypothesis continues attracting attention in documentaries and public imagination, though most scientists do not currently treat it as the leading explanation due to unresolved evidence and replication concerns. This distinction matters deeply. A mystery is not the same as confusion. Scientists are not standing in darkness guessing wildly. They stand inside partial light. Enough evidence exists to understand much of the event, but not enough to remove every uncertainty. Perhaps the most honest way to describe the Younger Dryas is this: science knows the shape of what happened more clearly than the exact spark that began it, and that leaves a strangely human feeling lingering behind the evidence. How do we remember a mystery that is partly understood, partly unanswered, and still quietly unfolding through research today? Perhaps one of the quiet reasons the Younger Dryas continues attracting attention is because humans rarely feel comfortable with unfinished stories. We prefer clean endings. A problem appears, a cause is discovered, a conclusion settles everything into place. Mystery solved. Yet some events in history refuse to behave that way. The Younger Dryas remains strangely compelling not because science knows nothing, but because science knows enough to reveal how incomplete certainty can sometimes feel. Around 12,800 years ago, something interrupted a warming world. Evidence confirms it happened. Researchers understand parts of the mechanism, but the final trigger still sits somewhere between strong possibility and unanswered question. And perhaps that uncertainty explains why people continue returning to this story again and again. Humans have always been drawn toward mysteries that feel close enough to touch. A complete unknown often feels distant, but partial understanding creates tension. We understand enough to imagine clarity, yet not enough to fully arrive there. The Younger Dryas exists inside that uncomfortable middle space. The oceans may hold part of the answer. Ice sheets may hold another. Atmospheric feedbacks may matter. Even controversial ideas survive discussion because enough uncertainty remains to keep asking questions. This is not unusual in science. In many ways, it is how understanding grows. Early explanations rarely arrive complete. Evidence accumulates slowly. Competing ideas challenge one another. Better methods improve older mistakes. The picture sharpens, though sometimes never perfectly. There is a temptation, especially in modern storytelling, to mistake uncertainty for failure. If scientists disagree, people sometimes assume nobody understands anything at all. Yet disagreement often signals something more careful. When evidence remains incomplete, caution protects truth from becoming overconfidence. The Younger Dryas reminds us that honest science sometimes sounds quieter than certainty. Researchers often say, "This appears likely," "evidence suggests," or "questions remain." Those phrases may feel less satisfying than dramatic answers, but they carry something important: humility before complexity. There is something deeply human hidden inside that humility. Humans have always lived surrounded by forces larger than immediate understanding. Ancient people crossed landscapes without knowing how glaciers shaped rivers. Sailors crossed oceans long before currents were fully mapped. Farmers watched seasons shift without understanding atmospheric systems. Knowledge often arrives later than experience. The Younger Dryas sits inside that tradition. Ancient humans lived through climate instability without knowing why. Modern humans investigate the same event with laboratories, satellites, and climate models, yet still encounter limits. The difference is not that uncertainty disappeared, it is that humans learned how to question uncertainty more carefully. Perhaps this is why mysteries matter. Not because unanswered questions are frustrating, but because they quietly reveal how knowledge grows. Every ice core drilled, every sediment layer analyzed, every climate model tested becomes part of a longer conversation stretching across generations. Science rarely moves by dramatic revelation alone. More often, it advances through patience, small corrections, better evidence, questions surviving long enough to deserve better answers. And yet, even knowing this, people continue asking the same quiet question: why does the Younger Dryas feel so unsettling? Perhaps because it challenges something many people rarely notice they believe, the idea that tomorrow will probably resemble yesterday. Around 12,800 years ago, Earth briefly interrupted that assumption. Warmth returned after an ice age, then unexpectedly hesitated. Cold came back, landscapes changed, life adapted, certainty weakened. Which leaves us approaching the final stretch of this story with a gentler but deeper question. If uncertainty has always been part of being human, what kind of wisdom can still emerge from a mystery that refuses to fully explain itself? After everything we have traveled through, the Younger Dryas begins to feel less like a single event and more like a long, unanswered conversation between Earth and memory. We began with a strange contradiction. Around 12,800 years ago, the planet appeared to be warming after the last ice age. Ice retreated, temperatures climbed, landscapes slowly shifted towards something softer and more familiar. Then, unexpectedly, the trend hesitated. In parts of the northern hemisphere, cold conditions returned. A warming world suddenly turned colder again. Even now, thousands of years later, that interruption still feels quietly unsettling, because interruptions challenge confidence. They remind people that history does not always move in straight lines. Along the way, scientists uncovered fragments of explanation scattered across remarkable places. Deep inside Greenland ice, tiny chemical clues preserved signs of rapid cooling. Ancient lake sediments recorded changing environments. Ocean evidence suggested disruptions in currents that once carried warmth northward. Pollen trapped in forgotten landscapes revealed forests shrinking or changing course. Piece by piece, researchers reconstructed enough evidence to understand that the Younger Dryas was real, significant, and powerful enough to leave marks across continents. Yet understanding the event never became simple. The closer scientists moved toward explanation, the more complexity appeared. Meltwater from giant ice sheets may have weakened Atlantic circulation. Atmospheric feedbacks may have amplified cooling. Sea ice likely expanded. Ecosystems shifted unevenly. Some regions changed dramatically while others experienced subtler disruptions. Giant animals disappeared around the same broad period, though not always neatly or for one clear reason. Human communities adapted, adjusted, and continued surviving in landscapes that no longer behaved exactly as before. Again and again, the same lesson quietly returned. Earth rarely changes through one cause acting alone. Complexity hides beneath appearances. This may be why the Younger Dryas still feels strangely modern despite belonging to deep prehistory, not because it predicts our future and not because history repeats in perfect circles, but because it reveals something enduring about uncertainty itself. Humans often seek certainty as though certainty guarantees safety. We prefer clear explanations, one cause, one answer, one final ending. Yet much of reality seems less willing to cooperate. Sometimes understanding arrives incomplete. Sometimes several truths exist at once. Oceans matter, atmosphere matters, geography matters, human adaptation matters. Mystery survives not because knowledge failed, but because complexity resists simplicity. There is also something quietly hopeful hidden inside this ancient story. Around 12,800 years ago, people faced changing landscapes without understanding the systems shaping them. They could not explain ocean circulation or climate feedbacks, yet survival continued. Communities adapted. Knowledge passed between generations. Humans adjusted not through certainty, but through observation and flexibility. Perhaps resilience has always depended less on controlling uncertainty than on learning how to live beside it. Still, the Younger Dryas refuses to close neatly. Scientists continue researching sediment layers, refining climate models, and debating evidence. Questions remain alive because enough mystery still deserves patience. Somewhere beneath oceans, inside ice, or hidden within details not yet understood, parts of the story may still wait quietly. And perhaps that feels fitting for an event remembered not because it gave humans answers, but because it continues asking questions about climate, about stability, about how quickly familiar worlds can shift without warning, which leaves us approaching the final moments of this journey with something softer than certainty. If Earth once paused its warming long enough to surprise nearly everything alive, what does it mean to truly understand a world that has always been capable of changing more quietly and more suddenly than humans expect? Perhaps the most valuable thing the Younger Dryas offers is not an answer, but a habit of thinking. In a world that often rewards confidence, this ancient mystery quietly rewards patience. For thousands of years, the evidence remained buried inside ice, hidden beneath lakes, locked in forgotten layers of sediment no human could read. Only slowly did fragments begin revealing themselves. A clue in Greenland, a pattern in ocean records, signs of shifting vegetation, questions forming before answers arrived. Even now, researchers continue studying an event that happened nearly 13,000 years ago with surprising care. There is something meaningful in that patience. Humans often imagine learning as the moment certainty appears, yet much of understanding grows differently. Sometimes knowledge begins by accepting uncertainty honestly rather than rushing to erase it. The Younger Dryas may be one of the clearest reminders that asking careful questions matters as much as finding quick conclusions. Scientists did not stop searching simply because evidence felt incomplete. They continued comparing ideas, testing assumptions, correcting mistakes, and leaving room for better explanations to emerge. That process itself carries quiet value, not only for science, but for how humans think about complicated things. Perhaps this becomes the deeper educational lesson hidden inside the story. The world is often more connected than it first appears. Ice can influence oceans. Oceans can influence weather. Weather can alter ecosystems. Ecosystems shape animal survival. Human lives respond in return. One change rarely stays alone. The Younger Dryas reminds us that Earth behaves less like separate pieces and more like relationships constantly influencing one another. Understanding grows stronger when people resist the temptation to oversimplify. There is also a softer lesson about humility. Around 12,800 years ago, people lived through profound environmental uncertainty without fully understanding why familiar patterns changed. Yet they endured, they adapted, they learned landscapes again when old expectations stopped working. Modern humans often trust knowledge to remove uncertainty completely. But perhaps wisdom has always involved something gentler, learning how to live responsibly even when not every answer has arrived yet. Curiosity matters, flexibility matters, patience matters. In many ways, the Younger Dryas feels less like a warning and more like an invitation to think differently about certainty itself. The mystery remains unfinished, and perhaps that is acceptable. Some questions deserve time. Some truths emerge slowly. Even now, somewhere inside frozen records and buried sediments, details scientists have not yet uncovered may still wait quietly beneath the surface. One day, new evidence may reshape what researchers believe about why temperatures dropped so suddenly, or perhaps uncertainty will remain part of the story forever. Either possibility teaches something useful. Knowledge grows, but rarely all at once. And perhaps that is what makes history worth listening to before sleep. Not because the past gives perfect answers, but because it gently reminds us how much wonder still exists inside unanswered questions. Around 12,800 years ago, Earth briefly turned colder when warmth seemed ready to return. Life adjusted. Humans survived. Scientists are still listening to the clues. And somewhere between certainty and mystery, the Younger Dryas continues quietly waiting. Waiting inside ice, inside memory, inside questions not yet finished. Which leaves only one final thought to drift beside you tonight. If the world has changed suddenly before, and humans have always lived inside uncertainty without fully seeing it, how many quiet changes might already be unfolding around us long before we learn their names? Now, as this long journey through ancient cold slowly comes to rest, the Younger Dryas feels strangely quieter than when it first began. At the beginning, the mystery sounded dramatic. A warming world suddenly turning cold. Temperatures falling when warmth seemed ready to return. Oceans shifting, ice retreating, then hesitation. Questions large enough to survive nearly 13,000 years. Yet after traveling through the evidence, the theories, the vanished animals, and the people who quietly endured changing landscapes, something softer begins to remain. Not certainty, not even closure. Only perspective. Somewhere in the distant past, long before memory, the planet changed in ways no human fully understood. Rivers moved through colder land. Winds crossed landscapes already learning to become unfamiliar. Mammoths walked through grasslands that may have grown harder to predict. Small human communities followed seasons that no longer behaved exactly as older generations remembered. Nobody knew they were living through an event future scientists would one day call the Younger Dryas. Nobody understood ocean circulation or freshwater disruption. Life simply continued, quietly adapting to a world that no longer felt entirely stable. There is something calming hidden inside that thought. Human beings have always lived beside uncertainty, even when certainty felt close. Storms arrived before weather forecasts existed. Winters changed before climate records existed. Rivers shifted before maps could explain them. Yet people still crossed landscapes, shared knowledge, cared for one another, and slowly learned how to begin again after change. Perhaps history becomes gentler before sleep, because it reminds us that uncertainty has never meant the end of understanding. Often, it only means understanding takes time. Even now, deep inside Greenland ice, tiny chemical traces continue resting where scientists first learned something unusual had happened. Beneath lakes and oceans, sediment layers quietly preserve details no human voice can fully hear yet. Research continues patiently. Questions remain alive. The Younger Dryas still waits, not as a solved mystery, but as one of those rare moments in history where the evidence feels close enough to touch and still somehow slips gently beyond certainty. Maybe that is why stories like this continue following people long after they end. Not because mysteries demand fear, but because they awaken wonder. The earth beneath familiar routines has always been moving, adjusting, changing in ways too large to notice day by day. Mountains rise slowly. Oceans shift gradually. Climate sometimes surprises even the most careful observers. Yet through all of it, humans continue doing what they have quietly done for thousands of years. Watching, adapting, asking questions, trying to understand worlds larger than themselves. And so tonight, the Younger Dryas does not really end with an answer. It ends with a feeling. Somewhere around 12,800 years ago, warmth paused, cold returned, and something changed deeply enough that traces still remain beneath ice and stone. Scientists continue listening carefully. the planet keeps its older memories hidden patiently. And perhaps that is enough for now, to know that some mysteries are valuable not because they close, but because they stay open long enough to remind us how extraordinary the ordinary world already is. So as the story finally grows quiet, and the colder winds of deep history slowly fade into distance, one last question remains, drifting gently, without answer. If the Earth has always carried changes too slow to notice and mysteries too large to fully hold, what forgotten stories might still be sleeping quietly beneath the ground beneath our feet?